All right, in this example, we have a lot going on. It's a really important example because it pulls together a lot of the concepts we've been studying for the last 4 chapters. So it's going to involve both linear and rotational collisions all at once, and we're going to see what happens in terms of both the rotational momentum and linear momentum in the problem. So we are again looking at a situation where we have a mass m1 that is going to come straight in and hit the end of this bar and stick right to it here, right on the end. m2 is going to hit the bar and stick right to it out here. Comes in at this angle theta. The mass of the bar, we're told, is a uniform bar, so we're going to put the center of mass of the bar right at the center of the bar. And we're going to do it step by step, and I'm try to keep the explanation clean by only showing each part individually. The first thing we're being asked to do is simply to find the center of mass of the system based on the bar, mass 1, and mass 2. So what we know is that we have m1x1 plus m2x2 plus m3x3 divided by the total mass gives us the center of mass point. So m1 is at position 0. The mass of the bar is at position 1. And the mass of m2 is out at position 2. The mass of m1, we are told, is 1 kilogram. Mass 2 is 3 kilograms, and the bar is also 3 kilograms, so we get 7 on the bottom. When we calculate that out, we get 1.29 meters. So it's a 2-meter bar, 1 meter here. So 1.29 meters is going to be right here. That's the center of mass of the system. And remember, the center of mass of the system is nature's point of rotation. So this bar, as it says here, is, again, sitting on a frictionless table. So we're looking down at the bar. This bar is free to move. So when the collision occurs from the top, this bar is going to move down. And it's also going to rotate around the center of mass point as it's moving down on our page after the collision. So the next thing we are being asked to calculate is utilizing the the parallel axis theorem for the bar, and that's shown in a moment and shown on your page, to calculate the moment of inertia of this system of 3 particles, m1, m2, and the bar. And that's what we have here. So we would either know or be given that the center of mass, the moment of inertia for the bar about its center, given a uniform bar, is 1/12 ml squared. So we get the 1 kilogram meter squared for the center of mass of the bar. We're going to use the parallel axis theorem because the new center of mass over here, right, at 1.29 has an h in our parallel axis theorem, right? I parallel equals I center of mass plus mh squared. To get the moment of inertia of the bar about our new center of mass point, and then we just use mr squared for m1 and mr squared for m2 to get the total inertia value about our new center of mass point. So that's the moment of inertia about the center of mass point at 1.29, if you want to write that in, if that helps you out. So again, please feel free to pause whenever you need to pause. Get all of this down. Make sure you understand exactly what's in the problem, right? The 1.29 here is the radial distance from the center of mass pivot to M1. So from center of mass to M1 is the 1.29, and the 0.71 is from the center of mass to where M2 hits. So now we are going to look to find the initial angular momentum of the system just before the collision. And let's go to that. So I know you have some of this already drawn in. when the masses hit the end of the bar, so I'm talking down over here now, when the masses hit the end of the bar, right, this bar is going to, again, slide down linearly, but also rotate around our new center of mass point based on initial angular momentum of the system is going to equal the final angular momentum of the system. We assign the initial angular momentum for the point particles, so the part of their momentum that's going to contribute to rotation after the collision from R1 is going to be the 6.45, because we're going to do R cross P1. So as I just indicated, the R is the 1.29. Momentum P is mass times velocity, sine of 90 degrees in this case. When you do R cross P, that is going to be a thumb out of the paper. So that is why this is a positive value here. That's from the cross product. When we do the same thing for particle 2, now we don't have 90 degrees, so that's why I actually slid the R2 vector over and drew it from a common origin with the V2 value. So when we do R cross MV for particle 2, that's now a thumb into the paper, so that's our right-hand rule. Gives us the negative here, so that's where the negative comes from, the right-hand rule. So write that in if you think that's something that you will forget. Sine of 40 degrees is obviously from the cross product, and we get negative 2.738. Now the bar was initially at rest, so the bar had no initial angular momentum, so that was at rest, right? So the bar starts at rest initially. And here are the assigned angular momentum values we give to the linear momentum of the particles that come in, stick, and will contribute to the rotation. Notice the initial angular momentum is positive. Positive angular momentum corresponds to counterclockwise rotation. So conservation of momentum, we already have that answer then. Conservation of momentum tells us we are going to have counterclockwise rotation. So after this collision, right, the M1 collision overpowered the M2 collision to drive this rotation in a counterclockwise sense relative to our new center of mass. So again, I know there's a lot going on here. Pause the video whenever you feel the need. So let's take a look. I think the next two were short, so I have those both together. The initial angular momentum equals the final angular momentum. So we just calculated the initial angular momentum, right? Right here. That's the initial angular momentum. The positive is counterclockwise. The final angular momentum of the system is I omega, because now we have a composite system, right? So we know the moment of inertia of our composite system around our new center of mass is the 4.428. Omega final is what we're solving for, so we just divide by the 4.428 to get the omega final is positive 0.838 radians per second. All right, so that's it for the rotational aspect of the motion, but we said the particle is also moving translationally. So to do that, now we go back to what we've done in the past. So the 2 kilogram particle, right? So the mass M1, right? Mass M1 is, 1 kilogram particle. Mass M1 has no initial x motion, so that's why the initial momentum in the x direction is 0. Mass M1 in the y direction is mass times velocity 5 downward, and it's downward, so that's where the negative comes from. Now, for particle 2, we have to use sine and cosine. For particle 2, we have x motion based on the velocity cosine theta. So that's where the cosine 40 comes from. And we have momentum in the y direction, velocity sine theta, so that's where that comes from. So this is just taking the xy motion of the M1 and M2 particles prior to the collision. So that was the momentum that they had prior to the collision. Conservation, it's a collision, conservation of momentum. So there's our answer. We now know the final momentum of the system is equal to our initial momentum of the system. Momentum is mass times velocity. So the bar initially was at rest, so we had no initial momentum from the bar. Now we do have to be a little careful because the final mass of the system is the composite system, so it's all 3 times V final. So the final linear motion of this particle is given by 0.657 meters per second minus 1.265 meters per second. And the last little bit I have here is how much energy is there in this system after the collision that we would have to remove to bring it to rest. And that is just a reminder now to you that both rotational and linear motion are occurring at the same time. So we took our linear velocity that we just calculated. I took the linear velocity that we just calculated here and used Pythagorean theorem to get the speed. So that was the speed that the center of mass point of this composite system has. 1/2 mv squared over here gives us the joules that are in translational motion. We use the 1/2 I omega squared, where the I again is our composite I that we have calculated earlier in the problem. The omega, the spinning after the collision, we have here. When we put them both together, we get the total energy that's present in the bar and the two pieces stuck on the end, including both the rotation and translational motion. So if you were going to bring this system to a total stop, you would have to remove 8.662 joules of energy. So it's a very good problem. There's a lot going on in it. So I'll bring it down here one last time. Let me clean up all of the extra markings that I had on it, so you can pause it if you would like to pause it and get what you need to get down for your notations. But this really is a 4-chapter question, so that's why it was one of our longer lessons to go through. But we really understand a lot now about collisions and momentum and conservation.